So welcome everybody. This Friday we will give a lecture on symplectic geometry as an introduction to symplectic Dirac operators, because we are streamed to somebody whose knowledge on symplectic geometry is not known, so I dare to start with introduction really to symplectic geometry. So for me, symplectic geometry is strongly motivated by physics. Yeah. And I don't know whether you know it, so I will suppose I will start from some beginning. We will speak about three chapters: symplectic linear algebra, symplectic manifolds, and then motivation by classical physics. So for those you know it, you may do proofs of the theorems I will not prove and think of geometry, and think of other things to which it is connected. And I will give a homework at the end, so it will be a student seminar. Next time we shall read our process with symplectic bundles and symplectic Diracs, probably. Yeah, so we will speak with Valentina, who is the fifth of you who would like to listen to it. So first, I will start with symplectic linear algebra. So let us suppose V will be a vector space over R of finite dimension. Omega 0 is non-degenerate anti-symmetric bilinear form. And that's all, yeah. And such a form is called symplectic. What it means, non-degenerate. For any u not equal to 0, there exists, let's say, V in V such that omega 0 V uv is non-zero. So we do the same as in the case of Euclidean or symmetric forms. And the couple V omega 0 is so-called symplectic vector space. So first, what does it mean in basis? So let us have a basis of a vector space, how the form behaves, how the coefficients behave. So Fi, I is from 1 to k. Here, basis of V. We associate with coefficients which are just these numbers. parameters. And we would like to compute omega ji. Whether it depends, the question might be whether it depends on the basis of the property of the coefficients being antisymmetric, actually. So, does the property of antisymmetry of omega ij depends on the basis? So, what is omega ji or omega ij? Omega ji is just this. By antisymmetry, it is equal to minus omega 0, and this is by definition minus omega ij. What about omega ii? Omega ii is just omega 0 fi. Fi, which is minus omega 0 fi. So, sure, you can make one step further, make it, this is by definition of course minus omega ii, and now we would like to cancel by omega ii, but we are not allowed because we don't know whether this is 0. Actually, we would like to prove that this is 0. How do we do it? We add omega ii getting 2 omega ii is 0. In R we can cancel by 2 and we get omega ii is 0. So in the case of field R, we have here that omega ij are antisymmetric and omega ii is R0. There is a notion of a symplectic form for different fields than R, and especially in characteristic 2, you cannot cancel. So this is a small example that this field might be of some interest in number theory. We don't have it, this property. In general, and there exist examples that omega needn't be 0. What is very well known on symplectic forms lemma. So let V omega 0 be a symplectic vector space. Then the dimension k is necessarily even. How to prove this fact correctly? So let us compute the determinant of the matrix of the coefficients. This is by the previous minus omega ji is minus 1 to the power of k of omega ji, which is nothing but determinant of omega ij transpose, by definition of transpose. Another well-known but tedious fact that the matrix of determinant of matrix is equal to the determinant of the transpose, which is just this. Omega non-degenerate imply the matrix is non-degenerate. This is what I believe as an exercise. So we can divide it. We can divide this equation by the determinant of omega ij getting minus 1 k, the power k is 1, which implies that k is 2n. Is it correct? Okay. We should proceed with symplectic basis. So the basis of a vector space V equipped with the symplectic form is so-called symplectic if the matrix omega 0 fi fj is of this form. For example, there are also different notions of symplectic basis. So this is in contrary to the definition in Euclidean geometry or geometry with scalar product, vector space with scalar product, where the orthonormal basis is uniquely defined as a such basis for which the bilinear form is the unit matrix. Yeah, so here you have several choices. You can choose, some authors choose here minus, here plus, and also some of them choose minus ones around the main diagonals, up and plus here, plus down, or vice versa, minus here and plus here. So what is 1? I mean, matrix 1 is just this. So this is a mathematical choice, I would say, for physicists which choose minus of this matrix. For some reasons, I don't know. Existence. So let us suppose something more general. Suppose that we have a form omega, which is bilinear, anti-symmetric, but possibly degenerate and we suppose only that it is non-zero by linear form. So by the non-zero-ness, there exist vectors which we denote by E1 and En plus 1. For which the omega is non-zero. If there doesn't exist any such a vector, then omega would be 0. If there exists one vector only, let's say E, then omega EE is minus omega EE, thus omega EE would be 0. So there must be two distinct vectors for which the omega is non-zero. Okay. So E1 non-equal to En plus 1 by contradiction. Yes, so suppose there are not two differentiable, there is no vector, so this is then 0. The omega, and also for other reasons it is 0, because of antisymmetry. Suppose there is only one vector, E, but then omega EE is 0, because omega is antisymmetric, omega E is minus omega EE. Meaning omega E is 0. Moreover, En plus 1 and E1 are linearly independent. So let us define such a subspace. If En plus 1 or E1 is a multiple of E1 or En plus 1, then omega E1 En plus 1 is just lambda times E omega E1 E1, which is 0. So we have a two-dimensional subspace, and we form a complement, a symplectic complement. B prime is a B prime, that is denoted by B prime. The complement is respect to omega, which are just vectors of V, such that omega are vectors V prime from V, for which omega V prime on V is 0 for all V in this E1. So I have to choose some notation regarding in order you can understand it uniformly. So what should be evident, and you may check it. That the intersection of E1 and the complement is 0. This is easy to compute by contradiction. Suppose that there is an element V prime from E1 and V prime and E1. So let us write it, and let us write it as a linear combination of the two vectors. So suppose that it belongs to the, I may write to the intersection, and then compute the scalar product of this V prime from V with E1 and with En plus 1. You get that A and B is 0. So exactly what is expected. Second information is that the vector space really decomposes in this way, in the complement and the two-dimensional subspace. This is done by a trick. V, any V can be written in this way. This element is second element. This is just writing null, writing zero in some different way. So this is from E1, and now you shall compute that the upper part is from B prime, and this you prove just by definition. Compute the scalar product of this first box vector, the vector in the first box is E n plus 1 and E1. Verify. By definition. So now point. Okay. Until yet it was quite easy, I guess. What do we do now? So probably we see already that we got to a lower dimension over which we do the induction. So now does restrict omega to B prime to times B prime. There are two possibilities. If it is 0, this one, or if it is non-zero. If it is 0, meaning this is 0, we get the matrix of omega is this. Stealing. No, I was wrong with the minus plus 1. This scale. So this is non-zero, it is mu, and take the n plus 1 prime, meaning 1 over mu. So we can assume this situation already in point 2. I didn't mention it already. In point 2 we can rescale. But we can rescale now getting such a matrix. It stays a basis. So a rescaling of non-zero number. The E n plus 1 and n. If it is non-zero, proceed to step 2. Yeah, so go to 2. Should be 1. And go to 2. And go further. So yes, okay. Oh, it should be okay. Up to ordering, which I will not mention. To sum up, we get vectors E1, En plus 1. Maybe we do it E2, En plus 2, E3, En plus 3, up to En, E2n. With respect to which the matrix of the omega has the following form. So here we get actually this matrix up to reordering the times, ordering them as it is written here. Otherwise you have E1, E2, E3, and you will get the matrix which has ones over the diagonal, up to the diagonal, and down to the diagonal. So there is also a reordering, which not up to you. I don't know whether one needs further induction in this step. Yes. Let us number these blocks. I mean, determine their size. I will put here the numbers. Q, R, RQ, RP. And Q is Q, P is Q. So this is let's say algorithm for a non-zero antisymmetric form, how to make it, if I may say, canonical somewhere. So this is the analogy actually of the Sylvester inertia law for bilinear antisymmetric forms, possibly degenerate. So this can be solved as Sylvester inertial law for anti symmetric forms. Existence of the symplectic basis comes here. Yeah. So the existence of the symplectic basis, real existence of the symplectic basis. We suppose now of the symplectic basis that omega is non-degenerate. In any case, we know that omega can be written as such by such a matrix. But such a matrix has a hull, a kernel, non-trivial kernel, which is spanned by vectors of such a form. I must have a look here. So So you can plug in the vector and get that it is 0. But the omega shall be non-degenerate, it shall have no non-zero vector for which omega evaluates as 0. And you can think of it from the left and from the right. They'll be multiplied from the left and from the right by anti-symmetry. So non-degenerate means R is 0. And we prove the existence of the symplectic basis. So we have the right matrix form. So this is crucial step in symplectic geometry. Symplectic linear algebra. There is also construction analogical to the Gram-Schmidt orthogonalization. This can serve in a similar way. So there exists a symplectic basis of any symplectic vector space. One can continue speaking about coisotropic, isotropic, Lagrangian manifold subspaces, but we stop doing that. We will just stop. I think it's these are the important things for symplectic linear algebra. So inertia law is a crown of the point of the highlight of this symplectic vector spaces. Uniformization. Yes, we will see it. How it applies further. So let us start with the second chapter, symplectic manifolds. Second part of the lecture. possible reference to it is Macduff and Solomon. Solomon. Do some Macduff and Dietmar Solomon. Introduction to symplectic topology. So a reference to the symplectic linear algebra may be Rolf Bern. The name is a bit strange. It is called symplectic geometry. Geometry shall, by some classical habits, speak about connections on vector bundles and geodetics. They speak about topology. But nevertheless, I will write it. This is just a philosophical approach. Rolfman. Introduction to symplectic geometry. So symplectic manifolds.
So it's the same brand and this one?
Yeah, they are possibly the same, but they don't have
the same Harrison.
They have double point and they don't have.
No, one has two.
One has a book and the second. One has a book and the second doesn't.
No, one has a book and the second has T, right?
T, yes, I don't know. What do you mean yet?
So which one has book?
This has book and this has what?
So these are two different people?
No, this is only one. I wrote it twice.
Because there is T and there is no T, so.
Aha, that's really, I don't know. So I will say it later to you.
This is most important for our lecture.
Really?
To distinguish between the two people.
I don't think so. So let M omega, let M be M manifold, smooth manifold, and omega will be antisymmetric two form. This is a classical notation. Suppose that for each point in the manifold, we are being precise, omega, the form in point M, which we denote by omega m, with lower index m, which is what, by definition, antisymmetric form on these vector spaces Tmn and Tmn, our vector space Tmn. And suppose that it is non-degenerate, which is actually something more than supposing that then it is antisymmetric two form. Yeah? So maybe I will use this notation for antisymmetric two forms. It can be used E2 in order remains you something from lectures you had. You might have. Antisymmetric, non-degenerate. And moreover, suppose that omega is closed. So, moreover, suppose So the non-degenerateness is in each point, yeah, so it is not the global versions of possible global versions of that might be different in different cases, because non-degenerateness means for any non-zero vector here, there exists something non-zero. But what if there is no non-zero global version of vector field on sphere? There is no everywhere non-zero. Further possibilities. So I chose out that. I hope it is not annoying preciseness, but let us suppose it. Does it make sense? So, closeness. Nobody studied physics, maybe Valentina did. This closeness is for some reasons from physics. Yeah. So somebody may ask why closed, but this area of math was, as far as I know, highly motivated by physics. And in physics, somehow we shall come to it. It speaks about Poisson brackets. Yeah. So let's mimic somehow Jacobi identity for Poisson brackets. So, but formally it is okay, it is defined, and so on. Examples. Easy. 2n-dimensional vector space. Why 2n? Because it's we prove it that at any point the vector space must be 2n-dimensional in order omega be antisymmetric and non-degenerate.
So M is a manifold of even dimension.
Yes, necessarily, yeah, because in each point we shall have a form which is antisymmetric non-degenerate, and we proved about any antisymmetric non-degenerate form that it must be defined on a 2n-dimensional vector space. R2n omega, these coordinates. First coordinates pi acting on endpoints and acting on further endpoints, which we denote in this way. So this is pi, and the function qi qj is q1 qn qj. So these are coordinates on R2n. In order to make it really unambiguous, one shall maybe underline some variables. We shall often not do it. Okay. Omega. So we take this, so in any point, what is easy, in any point, we get coordinates where fi's are, are vectors generated by the coordinates. So Fi. No. Yeah, okay, so.
So should it be underlined? Under the
No, this is not underlined.
So this is what?
This is just my notation that I just stressed it. Hopefully nobody stressed it.
I'm stressed totally, so.
Why are
What is under tilde? So this is also your notation. So this under
no,
tilde.
forget this
No,
double. This is double underline.
No, this under
No,
tilde.
we must continue. So yeah, so maybe everybody knows that, and I just record it. I hope that it reminds you something from Riemannian geometry, notation, and so on. I just. Second, sphere, round sphere. Yeah, what could be a symplectic form? So symplectic form, not on vector space, but symplectic form. This also gets forms of this coordinates. We search for a two form, which is non-degenerate. So and B can take the volume form of the round Riemann metric. This is given by some formula. Do you remember it?
Yes.
Yes.
Omega. d with d theta multiplied by
Sinus theta d phi d theta, for example, in some coordinates. But actually, sinus theta can be 0 in this case. So one must take.
In spherical coordinates.
One must take actually further atlases. And for proving that omega on other charts it's non-degenerate. Because here it is degenerate, theta is 0. No, but it is, you need everywhere non-degenerate, so it's forbidden that it is somewhere 0. So it is just
R theta and phi are global coordinates on R3. And the same for Twistor.
It is by restriction. Okay, so I will just say that it is a volume form. So any volume form is non-degenerate. And since it is a two form, making exterior differential takes it to three forms which don't exist in the case of sphere. The omega 0 for dimensional reasons. So this is just an illustration.
But if theta is 0, so this is 0. So
I know, you must take 3 different charts and to prove it in 3 Okay, but we will let it be. We have further nice examples, like torides. So that example, torides or tories. What is a torus? What is a torus? Torus in dimension 2n, it's a product of 2n spheres of dimension 1, 2n circles. And the symplectic form can be chosen as d phi I, d phi I plus n. Closeness also easy by Leibniz rule d omega is d square phi I wedge d phi I plus n plus minus 1 times the d on the second. So let us write it down. So this is easy. So torides are symplectic manifolds.
So is there some form which is close but not exact, like this one?
42s, for example.
For example, what?
42.
I don't care for any n, so is there some example of omega which is close?
Yes, but I don't have it in mind. So. Actually, not probably. I don't know it yet. Yeah. Well, this is this will be further topic. Yeah. So to speak about this, I don't have it in mind. We'll come to this when we will do cohomology, so, and it will be easy to decide it. So it is a question of multilinear algebra to compute the nth wedge product of omega. From non-degenerateness of omega, we get non-degenerateness of this highest degree form by induction. So it's well known, but formally it must be by induction. From this, we can conclude that any m omega is orientable. Orientability can mean technically only having everywhere non-zero section of the highest of the bundle of forms with the highest possible degree. Exists everywhere matic from M to this bundle. So this is by linear algebra. There are thus also non-examples, easily constructed non-examples of symplectic manifolds. Of manifolds which are not symplectic. So do you know some which are not oriented?
Real line.
A real line is not oriented. Is not symplectic manifold. By which admitters which are of dimension 2n?
No. Well, non-orientable ones, so projective space is real ones for everybody knows.
Perfect.
But this is the general knowledge. Exceptional.
2k non-orientable. RP1 in general R2k plus 1 are orientable. This is just a mnemotechnical rule. So because if you know that RP1 is a circle, so which is orientable, then you can deduce these informations. What is more interesting is this information. If M is symplectic, and M is compact, unfortunately. Compact. Then omega cannot be, it's not exact form. Meaning that it is not a differential of one form.
But that one, you find that one is not exact. That one on the top.
Which one?
That one. On the product.
This is exact form. This is not exact because you cannot have coordinates by phi 1 because they are non-continuous actually. So somehow contradict yourself.
What's that? Yeah, non-continuous.
Circle cannot be given just one chart.
But it might be the coordinate on the covering space.
You don't consider any covering space. It cannot. Well, it can probably.
So you find that that form is not exact. That one.
Try to find the preimage, the first integral. So what I have in mind is phi 1 d phi I plus 1.
Some phi I which d phi I plus 1.
Peter, so you are really too ahead.
This is just a simple question.
Yes, but I will come to it later. So we agreed that we will have 2 or 3 lectures, and we had only 1 last week. Strange. So, proof. So symplectic manifolds are orientable. Why not to compute their volume form? A volume. This is just up to a constant. For contradiction, suppose it is exact. This should be set at the beginning, actually. So let us write it. What it means. And now try to say that this somehow further exact, meaning can be this. It's very easy for mathematicians, so we can write it in this way. Writing the manifold in this way, yes. And this is just by Stokes' theorem, abstract Stokes. Let's say abstract Stokes' theorem. Just this. But manifold classically, I didn't say, but we suppose it's standard here has no boundary. This is 0, which is then absurd, which is impossible, since the volume of an orientable manifold is not always non-zero and positive. So let us solve the question of spheres, not of the torides, but of spheres. Question: does S2n admits a symplectic form meaning does S2n be the S2n omega be symplectic manifold? S2n compact. That the proposed omega, let us denote it by omega. The proposed omega cannot be exact. It's not exact. It's not exact. This has to be a non-trivial space. Otherwise, if it would be zero, then any closed form would be exact, and symplectic cannot be exact. And suppose that the symplectic exists. What is Dirac cohomology group? This is defined actually here. This denotes Dirac differential on two forms and this on one form's numbers. Now then, written well. Then you know from algebraic topology, from analysis on manifolds and algebraic topology, that these two groups of singular cohomology and Dirac cohomology are equal, and you know the cohomology of the spheres, probably. Yeah, so I will just mention this simple fact that this is zero if n is bigger or equal to 2. So S0 and S2 has non-zero cohomology, second cohomology. S3 has second cohomology already 0, S4 as well. So on S4 there cannot exist symplectic form. Answering the question also whether it can be a complex Kähler manifold, not because it is not symplectic. So this is the list of examples we had, and now let us come to a further question. On R2n we have this dp dq form, let's say, dpi, dqi, this lower and upper indices. Can there be another different, another symplectic form in R2M? Okay, the homework not yet. Sorry, not yet. I'm sorry. Yeah, so we finished the examples, and now, being categorical, we shall speak about the morphisms of symplectic manifolds. Definition. Having two symplectic manifolds, a diffeomorphism. Diffeomorphism is so-called symplectomorphism, or a morphism, categorically speaking, morphism of symplectic manifolds. If the pullback of the targeted symplectic form is the symplectic form in the domain. So, objects in the symplectic category are symplectic manifolds. Symplectic objects in symplectic category. Morphisms as defined above are called symplectomorphism. Morphisms. Two manifolds are called symplectomorphic if there exists a map phi. Symplectic manifolds. Symplectomorphic. If and only if there exists phi between them, which is a global diffeomorphism. Onto. So this is symplectic equivalent, this is orthogonal, this is rather very standard. Also using symplectic geometry. So does it make sense, this information? A good reference for this are monographs from Weinstein. Symplectic degrees. I write it only in this way. See, Weinstein. I mean, that's literature. So now we can ask a question. And we restrict ourselves only to dimension 2. Yeah. R2 is omega dp1 lower index dq1 upper index was introduced in point 1. I mean point 1 of examples. For simplicity, let us write it in this way. Does R2 admit any further symplectic form is easy question, because you can always multiply it by non-zero number, for example. Or you can do a symplectic change of coordinates, which we just might guess that it's connected to symplectomorphisms. But there shall be something, I mean a differential form, which is closed, antisymmetric and bilinear, such that the R2 with this form, the Cartesian plane with this new form, is not symplectomorphic to that. R2 equipped with omega prime symplectic form as a manifold as an symplectic form. On manifold R2 and R2. So in each point it shall be symplectic. Yes. Not doing translations. I'll make this interesting, but a bit detailed construction, which actually is connected to what you imagine above manifold R2 is translated into vector space. So if you can find something, if you can say it, yet you can. But let us postpone it for next time. Yes, we'll try to find out any symplectic form such that this form is non-symplectomorphic to this, with the manifolds are non-symplectomorphic. You can guess it, and then you can also send an email to me whether it's a right candidate for being non-symplectomorphic. Or you can prove it by yourself. So, second chapter of today is, which I almost omit, is classical physics. so-called non-quantum Hamiltonian. So classical approach is that we have impulses, coordinates written in this traditional way. One of the ways this is more traditional, and we have a Hamiltonian R2n, which is something like only smooth function on R2n. Smooth function. Then one speaks about Liouville form. I will try only to define it in order to understand it. Yes, probably in this form, but sometimes it might be multiplied by this. Then the equation of motions are dh dt I in the point which I specify for definiteness d1 t q and t are qi's in point t, where each t is from each number from 1 to n, and dh dq b1 t until q and t is plus minus minus b I t. So these are the Hamiltonian equations for a curve which I might specify gamma t is p1 t until p and t from q and t, q and t. So how to put it in the realm of symplectic geometry, or what we told already, and how to put symplectic geometry, better to say, to connect it with these equations. So, definition for physicists and for those who would like to learn it, definition if m omega is symplectic and h is a smooth function on the manifold. Smooth manifold. Smooth manifold, smooth function. Smooth function. Then m omega h is a Hamiltonian system, just this. We would like to capture the structure of the equation of the equations above. Oh, and there is a mistake. I forgot to write something. I'm going out of time. Here is a prime and here is a prime. Thank you. These are ODEs, actually. For the PIs and QIs, for the gamma curve. Yeah. So we would like to geometrize the situation of ODEs. Let us write these for these partial derivatives by gradient, by differential. So let us for differential of h, and let us take a dual to it in the second coordinate. No, in the first. I managed it yesterday. So omega evaluated in xh, which we now define, is minus dh on y on n for any y. So this defines xh a vector field on M. Yeah, if this is satisfied for each y. Why is this true? Peter, why this is true? Because omega is not degenerate in each point, so in each point we just get dual to the bilinear form in the point. And actually the vector field. So for each y, this shall be true. And x h m y m is just minus dh y m, where dh is a linear form in the point M. So, and now what one can do, one can search for integral curves. So let gamma be a curve on a neighborhood of 0, traditionally, such that gamma prime t xx, if this xh in point gamma t, I can evaluate it here or here. But the same, just the notation, to recall the notation for forms evaluated in point. Then gamma is a Hamiltonian curve. So to verify that it is equivalent, one needs to go into coordinates and to reprove it in geometry, which might be a homework as well. Yeah, so that this is equivalent if omega is dp dq and n is r to n. Yes. Further homework. Smooth function. Verify that the equations with differentiation of h are equivalent, are the same. equal. So this is what you can verify in this canonical situation. You can use the matrix. You can use the fact that the matrix is this plus minus all this omega. So if you would like to do it. So that's all for the motivation. I have only one example here of oscillator, and I hope that we can manage it next time, so-called harmonic oscillator. So that's all. Sorry for being a bit late. I hope it was a brief introduction, and that you enjoyed it in apostrophes. But any questions? Are there some questions? Are there some questions?
Well, I would say, for the rest, if you do not understand what was written before on the previous, so the previous definition, when you have symplectic manifold and some function, blah blah blah. So we have classical problems that if you have a smooth vector field, so you would like to find its flow lines. How you can do that in symplectic situation? So you don't have anything like you pretend you don't have anything like vector field. So if you have function h. So what you do, you can differentiate it, you will get a one format in vector field, you have to call that
you can do the same what I did.
Using omega. And therefore, the corresponding equations for the flow lines, that system is split into the system of two equations I'm trying to explain. On the right hand side, there is a derivative not of P and Q as in the classical case, but you have to apply J again, so the transformation is by omega. So you swap on the right hand side of this differentiation along T, Q's for P's, and you to half of them you put